class, this is summary video number 7, which is about natural convection chapter. For this chapter, the first item we investigated was thermal expansion coefficient, which was beta. And we investigated the formula for beta, which was derivative of density over temperature, or volume over temperature, so it will be same. So, and we find out for some liquids or fluids, it can be positive, it can be negative. For ideal gas, I proved we can use 1 over T, and the unit is going to be 1 over Kelvin. But if it's liquid, you need to find from tables. And this thermal expansion coefficient is going to be very important later when we be extracting buoyancy force for natural convection flows. Then we started working on the simple case of a vertical wall at a constant surface temperature T infinity, and the surrounding temperature of the fluid wall Ts, and the surrounding temperature of the fluid wall T infinity. And we showed we have thermal boundary layer, temperature profile, thermal boundary layer, and velocity profile there. And we extracted formula, which includes a convection term, diffusion term, and we call this one buoyancy term. And when we try to solve this partial differential equation, we reached to the dimensionless number, which we called it Grashof number, which was G beta delta T characteristic length cube divided by kinematic viscosity power 2. And how we got that? And basically, that Grashof number was the coefficient of temperature, dimensionless temperature, divided by Reynolds number power 2. So we had this Grashof number divided by Reynolds number power 2 as a coefficient of dimensionless temperature. And we talked if this portion, this coefficient was really smaller than 1, we can say natural convection is negligible. If it's really larger than 1, we can say natural convection is dominant. And if it's equal 1, we can say force and natural convection is going to be both important, and we need to consider. Then we talked about Rayleigh number, which was Prandtl number times Grashof number. And why we defined it? Because we usually have Grashof number times Prandtl number. That is why Rayleigh number is defined, and we are going to use this Rayleigh number mainly to identify what type of flow we have. For external internal flow, Reynolds number was the critical parameter to investigate if we have laminar or turbulent flow. Here, it's going to be Rayleigh number because the driving force, which is temperature difference or density difference, is inside the Rayleigh number formula. Then we moved on to different geometries, and we investigated a few of them. For example, if we have vertical wall, that characteristic length we need to select is going to be L. And then for different Rayleigh range, we introduced several formula. For the vertical wall, we said you only permitted to use the third one because it is much more accurate, and we're going to use the other two. If our wall is angled, the only difference is going to be using, instead of G, which is the gravity, you're going to use G cosine of theta. Be careful, that theta is going to be from the vertical line. So this angle is going to be theta. Be careful not to use the other side. And theta should be between 0 to 60. For horizontal upward or downward, the only difference, important point, was characteristic length, which is the surface area divided by circumference. So you need to consider that one. And for different range of Rayleigh number, different formulas, Nusselt number formulas given. For the cylindrical shapes, if it's vertical, we don't have formula. So you need to consider the diameter of that cylinder. If it was larger than this portion, you can consider that cylinder as a vertical wall and use the vertical wall formulas. For the horizontal one, another formula is given. And for sphere also, there. Again, many students forget about this. If the cylinder is vertical, the characteristic length is going to be L, because we are going to use as a vertical wall. Otherwise, we don't have any formula for vertical cylinder. Or you need to find from the other from literature. It's not in our textbook. This is for all the cases when we had a wall with a constant surface temperature. If we had a constant heat flux, it would be a good approximation if you select the temperature at the middle height of that wall as a surface temperature. So imagine if we had a vertical wall with a constant heat flux Q dot, I'm going to find the temperature of that surface at the middle height, T at L divided by 2, and it is going to be my surface temperature. Then I'm going to use the surface temperature to calculate film temperature and the rest of the stuff we are familiar, and use all the formula suggested for surface with a constant temperature. Okay, let's move on. We have introduced other formulas for different geometries. For example, if we had a heat sink, we can calculate Rayleigh number for heat sink. As you can see here, the characteristic length we use is S, which is a fin gap here. This is your choice. Sometimes people use L, which is the length of the fin, as a characteristic. So whatever characteristic length you're using, you just need to tell us this Rayleigh number is based on L. This Rayleigh number is based on S. So you use the characteristic lengths you want, and then mention it, what type of characteristic lengths you have. And we have some studies to generate Nusselt number, and for other condition, you can see the rest of formulas. If you had enclosure, which means it's a closed surface, we don't have any open surface. We can have left side one temperature, right side another temperature, and natural convection happening inside that. You can see we define Rayleigh number, and we have some formulas introduced for Nusselt number. If it's, for example, cold is at the bottom and hot is at the top, we're not going to have any movement because hot is going to stay at hot fluid is going to stay top and cold at the bottom, so no movement. But the other condition, which is the hot surface at the bottom and cold surface at the top, we are going to have some type of natural convection happening there. Or again, this is similar arrangement and for different Rayleigh number, we have different Nusselt number introduced from different studies. So you can see even if our enclosure is angled, we have many formulas introduced for Nusselt number, and for cylindrical coordinates, cylindrical geometries, again, other formulas introduced. For sphere, there are some. And if you want to investigate these geometries, try to solve one or two examples and use these formulas and get used to these types of formulas. Then sometimes we have both effect of natural convection and forced convection. For example, here you can see we have forced convection and natural convection both at the same direction. If you want to, you need to investigate the heat transfer rate, and the combined effect is going to be important. So basically, I'm talking about Grashof number over Reynolds number squared is about 1, so both they are very important. You can combine the Nusselt number from the force flow from the previous chapters, whatever you found Nusselt number. From this chapter, you calculate natural convection Nusselt number, and then you combine them. If they're in the same direction, add to each other. If they're in opposite direction, subtract from each other, and use this formula to get combined Nusselt number, which will be a little bit more accurate, including the effect of force and natural convection. As you can see, this n value parameter, sometimes we use 3, sometimes we use 4. And as you can see here, it is observed that n equal 3, correlate for experimental data, vertical wall. If you had a horizontal wall, you can use larger n. But usually we use 3 for our calculations. And yes, that's it. And see you next time.